Hello dear students. So, we will continue the discussion on the curvature and the solute effects. So, we will try to see how does the solute effect play an important role in deciding the growth of a cloud droplet into a rain droplet, or let us say into a larger or into the formation of a ice crystal, let us say. So, like we have seen several number of times. So, for the vapor to condense into a liquid phase, we will need what we call as the cloud condensation nuclei. Right. So, what are cloud condensation nuclei? Cloud condensation nuclei are a class of particles, or a class of aerosol particles. They make some of the, let us say, aerosol population. So, there are three different types of cloud condensation nuclei, which are, let us say, Atkin nuclei, which are typically of the size of less than 0.2 micrometers, and large nuclei, which are between 0.2 to let us say 1 micrometer, and another giant nuclei, which are greater than 1 micrometer. Now, what if you have this nuclei, we have to understand how the saturation vapor pressure with the solute varies or changes in comparison to saturation vapor pressure over, let us say, over pure surface, pure or let us say pure water. We have to understand how this changes. Now, what is the aspect that you want to understand when you add a solute? So, water impurities and their effect on the water evaporation rate is the basic idea. So, when you add some impurities on the water, what will happen? So, the impurities that I am talking about are the cloud condensation nuclei. So, if we have cloud condensation nuclei and condensation happens out of it, how will the vapor pressure change? Okay, some solute molecules occupy the surface sites that would otherwise be occupied by water molecules. So, why are we interested in vapor phase? So, the evaporation rate depends on the amount of condensation and the amount of vaporization, right. So, if we say that if you replace some sites on the surface, because ideally the surface molecules are the ones which will be escaping or which are free to escape into the vapor phase. So, if you replace some molecules with the solute molecules, let us say impurity molecules, then obviously the rate at which the evaporation takes place will decrease. So, thus the solute prevents water molecules from evaporating from those sites. Now, if you adding more solute means that more surface sites would be occupied by the solute molecules, and water vapor would eventually have less opportunity to break the bonds and go into the vapor phase, right. So, thereby by adding a solute, you are decreasing the rate of evaporation. We do not talk about temperature here, but at any given temperature, if you add impurities, the rate at which evaporation will happen will decrease. Simple. Now, because the evaporation rate is lowered, which means that there will be net condensation until the water vapor flux to the surface matches the water vapor flux leaving the surface. Right. So, when the equilibrium is established between the lower evaporation rate and condensation, the condensation will obviously be lesser. This means the water vapor saturation vapor pressure will be lower than what used to be only in the presence of water. Right. So, thus the equilibrium vapor pressure is less than the saturation vapor pressure with a pure water surface, right. So, flat surface of water, of course. So, as the amount of solute is increased, the equilibrium vapor pressure of the solution becomes even lesser. So, let us quantify this equilibrium vapor pressure over a solution. So, let us see how we can put these effects into a mathematical treatment, and how we can write an expression for the saturation vapor pressure with impurity in terms of saturation vapor pressure without impurity, right. So, then an empirical relation expressing this variation is given by the Raoult's law, right. So, we already have a relation, let us say. So, empirical relation expressing this variation of we have seen what it is, right. So, here E prime is the new saturation vapor pressure in the presence of a solute, right. Es is the saturation vapor pressure in the absence of a solute or in pure water, right. And chi W is the molar fraction of water. So, chi W will tell you what is the molar fraction of water, that is number of moles of water with respect to number of moles, the total number of moles of, let us say, solute and water, which is the solution, total number of moles of the solution, right. So, this is the saturation vapor pressure with respect to in the presence of a solute, and this is in the absence of a solute, where NW is the number of moles of water, NS is the number of moles of solute, right. So, if we continue this, so what we have is this is how an empirical relation. So, this is an empirical relation. So, this relation needs to be substituted with this, right. So, this is the Raoult's law. So, where we have approximated this molar fraction NW by NW plus NS as 1 plus NW by NS. Now, let us say we take a very dilute solution where the number of moles of solute are very, very less in comparison to the number of moles of water, very dilute solution. So, you have added a little impurity into the solution, right. So, chi W, the molar fraction, chi W is the molar fraction, can now be written as, so chi W can now be written as NW by NW. So, this is now written, this is now used here, right. So, then we can write it as 1 minus NS by NW. Now, we can use the Taylor series expansion to reduce this. So, the number of moles of solute can be written as number of moles of solute. What is number of moles? Weight divided by the molecular weight of a particular substance divided by the molecular weight of that substance will give you the number of moles. Now, if when you add a solute, when you add a foreign substance, it may so happen that this substance may dissociate. Let us say if you take NaCl, it may dissociate into Na plus and Cl minus. Right. So, this dissociation or the number of species that come out of the dissociation can be characterized by the degree of dissociation, degree of ionization or degree of dissociation, let us say. So, the number of moles of solute can be written as Ns is I times Ms by Ms. Ms is the molecular weight, weight divided by the Ms is the capital Ms is the molecular weight, where I is the degree of ionization or the number of ions every solute molecule will dissociate into. So, in this case it is 2, that means the solute molecule, which is NaCl that you are adding, is dissociated into 2 ions, which is Na plus and Cl minus, right. So, Nw will stay the same. Nw is the number of moles of water, is the amount of water and the molecular weight of water. Substituting these two things. So, now we need Ns and Nw. Ns is now written as I times Ms by Ms. That means that, so if it is, we are not bothered about what is the ion, which one is heavier or which one is lighter. We are just bothered about the number of species which will be available, let us say, in terms of its molar fraction. So, let us say if you add NaCl, NaCl will not be as it is. NaCl molecule will not be the same when you add it in the water. So, it will be Na plus and Cl minus. So, eventually you have an atom of Na plus, you have an ion in Na plus and you have an ion which is Cl minus, and the other molecule that you have is H2O. Right. So, if you substitute these two things here into the molar fraction chi W, you write, so you have Ns which is written like this and you have Nw which is of course written like this. You substitute these two things, let us say 1 and 2 into this expression which is A, let us say. So, chi W is 1 minus I times Ms by capital Ms into Mw by small mw. Right. So, now what is this? This is just a molar fraction and we are still wanting to write an expression for the saturation vapor pressure in the presence of a solute with respect to the saturation vapor pressure in the absence of a solute. So, now let us say we have this water as a droplet which has a radius r, and then in the mass of the droplet mw, we are trying to get the mass of the droplet, where rho l is the density, and if the droplet is at a with a radius r, so we can write that rho l, so chi w, we substitute mw, for mw we substitute this, so mw we substitute into this, so chi w is 1 minus I is the degree of ionization, ms is the mass of solute, times 3 m capital mw, mass molecular weight of water, divided by 4 pi, r is the droplet's radius, rho l is the density of water, capital ms is the mass molecular weight of the solute, right. So this can be simply written as something, let us say this, all this, which can be constants for a given solution. So chi w can be written as 1 minus b by r cube. So all this is I am calling as b, and r cube remains, such as I ms 3 mw by 4 pi rho l ms is going to be called as b. So now we substitute this into the empirical relation that we have, right. So E prime divided by Es is 1 minus b by r cube. So this is 1 minus. So in the case of solute effect, in the case of curvature effect, we see that the saturation vapor pressure over a curved surface in comparison to saturation vapor pressure over a flat surface was something like this, 1 plus. That means saturation vapor pressure over a curved surface will always be larger than the saturation vapor pressure over a flat surface. So here you see the exactly opposite. The saturation vapor pressure with respect to the solution is 1 minus. That means it is going to be lesser than pure phase. Why? Because there are more number of foreign molecules which are avoiding the water to evaporate, so thereby reducing the saturation vapor pressure. So we can say that the presence of solute will decrease the saturation vapor pressure. The reduction in the saturation vapor pressure away from the pure water due to the presence of solute is called as the solute effect. Now we have eventually seen how we can write the saturation vapor pressure over a plane surface of water, right. So this is what is called as the solute effect, right. So the presence of solute molecules in the heterogeneous nucleation, the presence of makes the saturation vapor pressure decrease. So one thing for now what we can say is that due to the curvature effect, the saturation vapor pressure, let us say Es, is increasing, and due to the solute effect, the saturation vapor pressure is decreasing. So are these two effects important independently, or are these two effects exist always together? That is the question. The question is, can you achieve nucleation? Let us say, can you think of a scenario where you achieve nucleation despite the lack of impurities? Yes, but ideally no, because nucleation can only be achieved at relative humidities which are like several hundreds, which are practically not possible, right, which are practically not possible in the sense that how would you be able to create relative humidity of 400% or 500% in an air parcel which is suspended in the air? At any given time, the air parcel can never be free of any particles. The moment you have the particles, 100% or 90% will still be sufficient to create nucleation. So in any given situation, the saturation vapor pressure is always going to be influenced with the solute. That means it will decrease as a result of the cloud condensation nuclei, and at the same time, when the condensation happens over a surface, over a particle, the condensation happens to result in the form of a droplet, and when a droplet forms, the evaporation will increase. That means having the cloud condensation nuclei decreases the rate of evaporation from the droplet, and droplet being present in the form of a sphere will increase the evaporation, right. So this droplet being present in the form of a sphere will increase the evaporation, right. So these two effects will always be together, but how does it matter to us? I mean, our process, our idea is to understand how the smallest cloud droplet will grow by diffusion by collision or by coalescence into the huge rain droplet. Right. So, if you put these things, if you want to understand how this growth happens, it is very important that how there are two processes which one is aiding the growth. One is aiding the growth by not allowing the water to evaporate, which is the solute effect, and another is hampering the growth in the sense that it is allowing more evaporation. So, more evaporation happens, the droplet will not be seen. I mean, droplet will evaporate. It will just vanish into the thin air. Right. Now, we have to understand how the diffusional growth of a cloud droplet can be achieved if you have these two intercompeting processes in the picture. Right. Now, let us for example, for a simple example, so we can always say that the radius of the cloud droplet, let us say the radius of cloud droplet is let us say in the units of let us say the radius of cloud condensation nuclei is 0.1 micrometer. The droplet will be of the order of 10 micrometers, the cloud droplet. Now, this has to grow to the sizes of let us say 50 to be called as a large cloud droplet, and this has to further grow to the sizes of let us say 1000 micrometers to be called as a rain droplet. Now, once this process is complete, only then you will see what is called as the precipitation. This is when the gravity kicks in and makes the rain droplet travel towards the surface, right. So, this process, this from starting from 0.1 to 10 micrometers to 50 micrometers and 1000 micrometers is the process which facilitates the precipitation, right. So, now we will see how this growth of cloud condensation nuclei acquires moisture and becomes a cloud droplet, then it becomes a large cloud droplet, and then it becomes a rain droplet. So, we have two processes which are, one is aiding the process, one is aiding this transformation, and another is hampering the transformation. So, the process which is aiding is the solute effect. Of course, solute effect is helping it, and the curvature effect. Now, let us try to combine these two effects and try to see mathematically what the relevance is. I mean, how the overall saturation vapor pressure changes with respect to plane surface or curved surface, and in the presence of solute and in the absence of solute. Okay, so let us say we will write, let us say the Kelvin's equation Es of R by Es of infinite is equals to exponential 2 sigma by R divided by rho L RV T, and the solute effect Es prime of R by Es is 1 minus I ms 3 mw divided by 4 pi rho L ms. So, this is what is this doing? This is increasing the saturation vapor pressure, and this is decreasing the saturation vapor pressure. Let us try to combine these two equations. Okay, so simply speaking, so we can write Es prime divided by Es of R as written, it can be written as 1 minus b by R cube, and Es of R divided by Es of infinite as exponential A by R. So, we have called everything this as A. Okay. So, for a very small radius of curvature, we can write exponential of A by R as 1 plus A by R. Right. Now, we can combine these two. So, our objective is to write Es, let us say star of R divided by Es of infinite. So, what is this? Equilibrium saturation vapor pressure in a solute over a droplet. So, that means we have taken both effects into consideration. So, how does the saturation vapor pressure changes in the presence of a solute over a droplet in comparison to equilibrium? This is Es of infinity. equilibrium saturation vapor pressure over a plane surface of water, right. So, we can write that Es of Es star of r divided by Es of infinite is equals to Es star of r divided by Es of r into Es of r into Es of infinite, which is 1 minus b by r cube into exponential a by r, which is 1 minus b by r cube into 1 plus a by r, which is Es star of r divided by Es of infinite is equals to 1 plus a by r minus b by r cube, right. So, this is the combined effect of where, so A represents things in curvature term and B represents parameters with respect to solute, right. So, this is the basic idea. So, where we have summarized the both curvature effect and the solute effect, right. So, now the point is we will try to understand more about this equation, the final equation, which is 1 plus a by r and 1 minus b by r cube. Now, the most important thing is this seems to be dependent inversely along, let us say, one term along 1 by r and 1 by r cube. Okay. Now, we will try to understand more graphical implication of this, and probably by combining the solute and curvature effects, right. So, here we can stop here. So, that means that we have seen what is solute effect, what is curvature effect, what is the importance of these two effects in the formation of Rhine droplets, or in the transformation of a single nucleus to the Rhine droplet, right. So, we will continue this discussion more to understand the diffusional growth of a cloud droplet.